In this video, we'll be learning about the load transfer mechanism, and we'll be learning how the loads are transferred between different structural elements, which structural elements carry the most loads and why. This will give you an insight as to how you should be designing different structural elements of varying strengths. And finally, we'll be correlating all the things we're talking about with STAAD model. So let's start off with the first thing itself as to how the load is transferred between structural elements. We'll go through an overview and then we'll jump into the STAAD Pro model. Right here, we'll be talking about the load itself first. Now, in general, the loads are categorized into 4 different types. That is the dead load, the live load, the wind load, and the seismic load. For our example, we are going to be only dealing with dead loads, and that too only with floor loads. This is being done just to simplify the outputs and make it easier for you to comprehend. Now, some of you do get confused as to why we are only talking about floor loads and why we are not taking self-weights, live loads, wind loads, seismic loads, etc. This is just an example. I want to show you what the values could be and what the values are coming out to be, and make it easier for us to calculate and for you to calculate. If I go and take in the self-weights and I take in the live loads and I take in the wind loads, it will be much difficult for me to give you what the value should be, because I'll have to go through the manual calculations and I'll have to do a lot of manual calculations. So just to make things simple, we are going to be talking only about the floor loads. That gives us easier calculations, and thereby it gives you a deeper insight as to what is going on. Once you get an understanding as to what kinds of loads are being transferred where, it is much easier to scale it up to self-weights, beam loads, live loads, wind loads, seismic loads, etc. So for our example, what we are going to be doing here with STAAD Pro, we'll be talking about only the floor loads in case of dead loads. Next up, we need to understand what are the different structural elements. Now, in general, there are going to be 4 structural elements. That is the slabs, the beams, the columns, as well as the foundations. Now, in some buildings, columns can be just columns or it can be shear walls. Foundations could be of different types. So we can have isolated footings, we can have combined footings, we can have rough foundation, mat foundations, pile foundations, and so on. But overall, these are going to be the 4 different structural elements in a framed structure. So now let's understand how the load is transferred between different structural elements. In general, in a framed structure, whatever load is coming onto the slab, which is usually going to be the self-weight of the slab itself, the ceiling plaster, the floor load, etc., is going to be transferred onto the beams. Whatever load is coming onto the beams, that is loads from the slab itself, as well as whatever load is there on the beam itself, is going to be transferred onto the column. From there on, whatever load is going to be on the column is going to be transferred down all the way to the foundation, and from the foundation it is going to be transferred onto the earth. So these are the 3 things which we'll be talking about, and let's directly jump into a STAAD model to understand how all these things work. So right here we have created 3 different models inside a single STAAD file. Now this is not usually advisable because you get disconnected beams, but anyways, this is just for an explanation. So you can see we have a structure type which has a 4x3 slab, and we have a 4 meter height frame. So all these are 4 meter each, and all these are 3x4 meters. If I go to the top view, you'll be able to see what I've done is essentially taken this and copied it 2 times. And what I've essentially done is taken this once and copied it 4 times. This is being done just to understand how the loads are being transferred on to the foundation finally, and which members are taking a lot of load. I'll quickly take you through the properties also. What I've done is taken a simple rectangular sections of 0.3 by 0.3, or rather 300 mm by 300 mm, and I have taken a material of M25. For the materials, I went inside the materials, created a new material called M25, which if I double click on it, what I've essentially done is just change the density, and I've changed the compressive strength right here. So this is the only changes which I have done. If I go to the support, I have a simple fixed support at the bottom. For the loading, what I have essentially done is I have created groups first. So if I go inside utilities and go inside groups, you can see I have created a lot of groups. If I'll just select one of these and just press on highlight, you can see this is one group, this is one group, and so on. So if I just go here, this is one group, and so on. So all the floors I've created as a group, and later what I've done is gone inside the load definitions, created just the dead load part as I said, and I've created different floor loads on different cases. So you can see I've created floor loads for each group. So what I've done is created a floor load of minus 10 kilonewton per meter square, and I've assigned it to all the groups, essentially all the floors. So this is what our structure is. I've already analyzed the file. For that, you can simply go to analysis and do a run analysis. I've already done that, and I have the STAAD run file available with me. Now, before we go into that, what I'll do is go inside the loading part again, and I'll just select one of these frames, and I'll go inside view and do selected objects only. So I just want to see this structure only. I'll quickly remove the node to node distances as well, so that it's much easier for us to see. Now, if I go inside loads now and just toggle on any of the loads, you can see this is how the load is being transferred. I'll first go to the top view just to show you how the load is transferred. Now, this is going to be a two-way slab. I've designed it as a two-way slab, thereby giving me the opportunity to transfer the load onto all the beams. So each beam right here, 1, 2, 3, and 4 beams are taking loads, which is described by whatever you're seeing right here. So this beam is taking this triangular load. This beam right here is taking the other part of the triangular load. This beam is taking this trapezoidal load, and this beam is taking this trapezoidal load. If I were to go to the front view, you'll be able to see what I'm talking about. What I'll do, in fact, is just select one of these floors only and go inside view and go inside selected objects and go to the 3D view. So you can see this part is taking this trapezoidal load, this part is taking this triangular load, this part is taking this trapezoidal load, and so on. So let's move on to the whole structure. Let's go back to this structure again, and I'll go to the view selected objects only. So now we understand as to how the load is being transferred from the slab onto the adjacent beam. So all these beams are taking up the loads in this triangular format. Next up, if I go to any of the beams, these beams are going to be transferring the loads onto these columns. So this beam is going to be transferring the loads onto this column as well as this column. Similarly, this beam is going to be transferring loads onto this column, and this beam onto this column, and you get the gist of it. That is how the beams are going to be transferring the loads onto the columns. Finally, if I were to say talk about this column itself, this is going to be taking the load of this beam, and additionally, it will be taking the load of this column also. So all the columns are going to be taking the loads of the beams just above it, as well as all the columns above it. So if I were to just go back to the last column right here, this is going to be taking the nearest loads, that is this beam and this beam, which in turn are taking the load from this slab in a trapezoidal format and in a triangular format. Additionally, this column will be taking up the load of this column, which in turn takes up the load of this beam and this beam and this column, which in turn takes up the load of this beam, and this column, which in turn takes up the load of this beam and this beam. So for the last column right here, you can see we are getting the load of all the entire floors above it. And that is why the columns at the bottom take the most loads. Beams do not. Beams just take the load of whatever floor they are at. And we'll be able to look at it when we go inside the analysis file. And that is what we'll do right here. We'll go over to the workflow and go over to the post-processing mode. I'll just quickly run the analysis and I'll go to the post-processing mode. So right now we are viewing just one of these structures, and let's keep it that way first. Now what we saw was that we had a 4x3. We have a 4 meter right here and a 3 meter right here. So we have a 12 square meter area, and we have a 10 kilonewton per meter square load. So essentially we are getting 120 kilonewton of load per floor. So each floor is giving me a 10 kilonewton per meter square load. Let's look at it from the point of view of reactions first. In general, what we are expecting is that we have 1 floor, 2 floor, 3 floor, and 4 floor, each with a value of 120 kilonewton, thereby giving us a total of 480 kilonewton load on the structure. Now, each load is going to be transferred equally, or rather this entire load is going to be transferred equally onto all these 4 nodes, or rather reactions, just because the structure is symmetrical. And if you don't understand that, I'll quickly take you to the top view again. What is happening for each of these members, or rather beams, is that this beam was taking just this load, this was taking this load, and each of these was taking the trapezoidal load. So if I were to just look at this node, or rather this column, the load transfer was going to be half of this entire triangle, because this beam was going to be taking the full triangle. So this part is going to be taking only this half triangle. Similarly, this beam was going to be taking the entire trapezoidal load. However, that was going to be divided equally into this. So you can see essentially we are getting a 4-part division. Each part is going to be taking different portions of the loads. Essentially, what we are getting is that the load is going to be equally divided into the 4 nodes. If I go back to the 3D view, and if I go back to the reactions, what I'm expecting is that the load of 480 is going to be divided equally on all these 4 nodes. So let's go to the reactions tab, and if I'll just zoom into it, I'll change this cursor quickly to a text cursor and just move these. So you can see each value, the Y value, we are getting a 120 kilonewton. So you can see Y value, we are getting a 120 kilonewton. That gives us a very easy comprehension as to how the floor loads are being transferred onto each of these nodes. So now you understand why I just took the floor loads, because it was much easier to get these values right off the bat. If I were to see the entire structure again, so if I just go to the whole structure, so what I'll do is just select this and go to view and view selected objects. So right here, again, all the values being the same, what we should be expecting is 120 load from this portion and 120 from this portion. So in general, we are expecting a 240 kilonewton force per floor multiplied by 4 number of floors. So we should be getting a 960 kilonewton. That is all well and good. Now, how is this going to be transferred downwards? Now, first of all, just before we start, you can see we are not getting exact values of 120, which we were expecting. And that is because the load transfer mechanism works in a way that tends to transfer a little bit of load differently. So let's for now assume this to be around 120. I will not go into the calculation part of it, but just understand that this value is close to 120, thereby a part of this. So we are getting each floor as 120, but the load transfer mechanism happens so that, or rather such that, the values differ a little bit. So we are getting a 120 value here, and that was expected. We are getting a 120 value here on this node, that was also expected. But what we are seeing right here, or rather on these 2 nodes, is that we are getting different values. So you can see we are getting almost the double of whatever we are getting here. Or in this case, let's think about it as 240. In these values, we are getting 120. This also we are getting 120, this 120, and this 120. But these we are getting around 240. And that is what we'll assume for now. Let's just forget about these 234. This is around 240. And that is happening again because of the same fact. That is, if I go to the top view. So if I were to talk about the floor load, this floor load was 120 multiplied by 4, that was 480. That is the floor load right here. This is 480 and this is 480. This node right here is taking 1/4 of this entire 480, that is 120. That is well and good. This floor right here is taking again 1/4 of this, that is again 120. That is also good enough. This node right here is taking 1/4 of this portion as well as 1/4 of this portion. That is 120 from right here and 120 from right here, thereby giving this value as a 240. Similarly, if I were to talk about this node is taking 1/4 of this, that is 120, and 1/4 of this, that is 120 again, thereby giving this a value of 240 as well. Finally, when we are talking about this node is again taking 1/4 only, that is 120, and this node is again taking 120, that is, or rather 1/4, that is 120. And thereby you can very easily comprehend, or rather see, that this floor right here is getting a value close to 120. This value again is getting this node is again getting a value of close to 120. These two because these are taking this floor and 1/4 of this floor as well, is getting almost the double of that value in both of these cases. Again, these ones are taking just the 120 value. Moving on quickly to the whole structure again, and let's just view this for now. So let's look at these reactions as well. Now this time we'll be going to use these values on the right side just to have a look, because it is very difficult to have these values looked at. So I'll just quickly look at each of these nodes. Now you might not be able to see the highlighted nodes. So what I'll do is go to the labels and just switch on the node numbers. So I'll just do that and click on apply, click on OK. So you can see this one is 103, and if I just select on it, you can see the 103 gets highlighted, and this will happen wherever I select the node. So you can see on the right side, the specific node gets highlighted. Now what we are interested in is going to be this vertical force right here. So if I just move on to the leftmost node, you can see this is getting a value of around 120. Again, we'll be forgetting about these slight value changes from 120. Again, this is because of the load transfer mechanism that happens in a frame structure. Let's look at this node again. And for that, again, I'll go to the top view and let's try to understand that. Once again, this node right here will be taking just this part of the whole equation. That is going to be, this entire thing was 120. So this is, or rather 480. So each value was 480. That is 120 multiplied by 4. This is taking a part of it. That is why we are getting a value of 120 here. For this node also, we'll get only 1/4 of this chunk. That is 120. This floor also will be, or rather this reaction will also be 120, just 1/4. This also will be going to be the 1/4 of it. That is 120. Things change where we are talking about, for example, this node, where we saw that this node was going to be taking 1/4 of this and 1/4 of this. That is, we are getting a value of 240 right here. Similarly, for this, we are getting a value of 240 right here. The same thing will happen right here, because this will be taking 1/4 of this chunk and 1/4 of this chunk, thereby giving us a value of 240. And similarly, for this node also, which will be taking 1/4 of this and 1/4 of this, giving us a value of 240 right here. This one right here, you can see, it's very easy to comprehend that this will be taking 1/4 of this, 1/4 of this, 1/4 of this, and 1/4 of this, thereby giving us 4 times the value, that is around 480. So this one is going to be around 480, and that is what we are expecting. So let's have a look at it and see what values we get. I'll just quickly go to the view and go to the 3D view. Let's select this. So the corners one, we are expecting a value of around 120, and that is what we are getting. So you can see we are getting a value of 119. For this corner right here also, we are getting a value of 119. This corner also, we are getting a value of 119. And the top corner right here also, we are getting a value of 190. If I look at these 4 corners or mid corners, we are getting a value of the double of that. That is around 240. So in this case, we are getting 230. Again, right here, we'll be getting 230. This one, we are getting, again, 250. And this one, we are getting 250. The middle one should be around 480. So if I just click on that center one, you can see we're getting a value of around 480. So this is how the load is being transferred from the top to the bottom. Now let's go on to a bit more specific results. For that, I'll quickly go back to the whole structure. So now let's look at the beams only. So what I'll do is go to the beam results. And if I were to just select any of the beams, we are getting different values. Now in beams, we are particularly interested in these Fy values and the Mz values, or rather, if I were to just increase the view this way and go to the front view, you'll be able to see that the bending moment diagram doesn't change from top to bottom. So it remains almost exactly the same. And if I were to zoom it even further, you'll be able to see that all these beams are having exactly the same bending moment diagram and almost the same values as well. So if I were to just select this value, you can see we are getting a Fy value of around 18. If I were to select this, again, you can see we are getting a value of around 18. This again 18 and this again 18. So nothing is changing from the top to the bottom. I'll go to the isometric view again. Each of these beams are getting almost exactly the same value of Fy. So you can see from the top to the bottom, nothing is changing. On this side, it will change, of course. The values are a bit different because the beam sizes are smaller. But again, moving from the top to bottom, you can see the values are exactly the same and at the right. The same goes for the case right here. If I were to select the outer beams, you can see we are getting a value of 18, again 18, again 18, and so on. The middle ones, of course, will be a bit higher. That is, we are getting 37, again 37, and if I were to move down, again 37, and so on. But the values from the top to the bottom do not change. Hence, what I'm trying to say here is that beams are always going to be taking the loads on that floor only and nothing above it. Let's move on to the column part. And for the columns, what we are particularly interested in is not this Fy force, but rather the Fx force, that is the axial forces. For that, what I'll do is just switch on to the axial force and just switch off this force. And I'll just reduce the graph size. By the way, I'm reducing the graph size by simply holding on to the control key and using the mouse scroll wheel up and down. This is a very quick shortcut of reducing the graph size. Alternatively, you can go inside, I guess, labels, go inside scales and do it from here. Or rather, I think so, you can do it from here. I remember this shortcut and I have not bothered to look at the labels one anyways. So just a simple view right here, you can see that the axial forces are increasing downwards. So if I were to look at this floor up top and just this column, you can see we are getting a value of 30. And this 30 is very easy to understand. We have a 120 floor load on this complete floor that is being divided into 4 parts. So we are getting a 30 kilonewton load on this column only. If I move down, now I'm getting the load of this floor, or 1/4 of this floor, that is 30, plus whatever was above it, that is 30 again. So in this case, you can see we are getting a value of 60. If I move down, I'll be getting 30 from this, and whatever was above it, that is 60 was above it, that is we are getting 90. And finally, if I move down, we are getting a value of 120. And this will remain consistent throughout. So in this case also, you can see we are getting a value of 30 for this one, 60 for this one, or around 60. In this case, the values are a bit different, but you can get the sense of it. This one is 90 and this one is 120. If I go to the middle columns, this will be slightly greater because this column itself is taking 2 chunks. That is, we are getting around 60 right here instead of getting 30. If I move down, we are getting 60 plus additional 60, that is around 120. Then we are getting again 160 added, around 180, and again 60 added, around 240. The same will be the case in this case also. For the corners, we are getting 30, 60, 90 and 120, or at least around it. The middle ones, we are getting again 60, 120, around 180 and around 240. The middle columns right here, if I'm able to select it, you can see these are getting chunks from 4 different floors. That is 30 from this one, 30 from this one, 30 from this one, and 30 from this one, thereby getting a 120 value. If I move down, this should be 120 plus 120, around 240. Moving down, this is 240 plus 120, around 360, and this one will be plus 120, around 480 values. So you can see all the values which we were anticipating is what we are getting. So coming back, going through the STAAD model, you understood what things were, how different structural elements took the load, and if I were to go back to how the load was being transferred, you can easily comprehend now that the loads are being transferred from the slab to the beams, from the beams to the columns, from the columns to the foundation, and finally from the foundation to the earth. Now, I did not talk about this too much because it didn't seem appropriate here. But anyways, the only thing we have to understand is that when it comes to slabs, it is only taking the floor load above it, or whatever dead load or live load is on that floor only. So it is floor dependent, or rather just whatever floor we are talking about. The same goes for the beams. So beams are ideally going to be taking the load of the beam itself and of the slab. But when it comes to column, this column is going to be taking the load of this beam plus columns above it, whatever columns are above it. And that is where we get a very nice picture as to how you should be designing your structural elements. The beams are ideally designed just for the floor load. Columns, however, should be designed ideally the strongest at the bottom and weak columns at the top, because that is how the loads are being taken. If you try to design all the columns as strong columns, this is not ideally helping, because this strong column is going to be taking load of just this slab above it. This one, however, will be taking this one, plus whatever floor is above it, this one, again, this one plus this one plus this one plus this one, every floor above it. So ideally, this column should be the strongest, and you should try to reduce the column size if possible. This will also give you an additional space at the top floors without doing away with the strength of the structure. So I hope you found this lecture interesting and valuable. If you did, please do not forget to hit that like button. Also, if you're not already subscribed to the channel, do subscribe. Thank you for watching. Leave any of your suggestions down in the comment box. I'll try to make a video on it. That's all from this video. I'll see you on the next one.